In this video, we're going to explore the concept of hybridization. So we're going to look at the ground state of carbon. So remember that carbon has one empty 2p orbital in its ground state. So if we broke up the electron configuration, we have 1s2, 2s2, and then if you divide the p orbitals into their x, y, and z counterparts, there's one electron in 2px, one in 2py, and none in 2pz. So there is one completely empty 2p orbital in the ground state. However, in the excited state of carbon, one of the 2s electrons will move up to the 2p orbital. So it'll look like this. So we'll have 1s2 and then one electron in the 2s and then one electron in each of the 2p orbitals. So this will make 4 single valence electrons, and that will explain carbon's ability to form 4 covalent bonds. However, in this state, the 4 bonds would not be equal in energy, and that's a problem because when carbon's making its 4 covalent bonds, they all need to be equal in energy. So this leads us to the concept of hybridization. So hybridization is when the orbitals blend together, so each is equal in energy. And this allows for bonding, and there are 3 types of hybridization: sp, sp2, and sp3 hybridization. The first example we'll explore is sp3 hybridization. That's when you combine one s orbital and 3 p orbitals, and that will give us a tetrahedral shape. Each of the orbitals will repel the others equally to give that tetrahedral shape. So if we take a look here, this is still carbon. Now it forms 4 sp3 hybrid orbitals. So we have our 1s2, and then we have 4 sp3 hybrid orbitals. So 1 s and 3 p's. So methane is an example that uses sp3 hybridization. So each of the sp3 orbitals from carbon will overlap with a 1s orbital from hydrogen to form sigma bonds, and the shape of the molecule will be tetrahedral. So here's the hydrogen sigma bond overlapping with the sp3 hybrid orbitals, like so. So that's methane. In sp2 hybridization, 2 of the 2p orbitals will hybridize with the 2s orbital, and then you'll have 3 sp2 orbitals. They'll be free to form sigma bonds, and the remaining p orbital will form pi bonds. So this type of hybridization occurs with carbon-carbon double bonds. So we have our 1s2, 3 sp2, and then 1 2p. So in ethene, each of the carbons is sp2 hybridized. So there'll be 3 sigma bonds formed on each carbon. So one with a hydrogen, another one with a hydrogen, and the third one will be a sigma bond with the other carbon. So we have 3 sigma bonds, but then we also have 1 pi bond with those overlapping p orbitals here. So we end up with 3 sigma bonds and 1 pi bond for every carbon. And that pi bond, remember, is overlapping of the p orbitals in a sideways manner, so not a head-on overlap. The third type of hybridization is sp hybridization. So then the 1 2s orbital will hybridize with 1 2p orbital, making 2 sp orbitals. This will leave 2 p orbitals unhybridized, which will allow for 2 pi bonds to form, which would lead to a triple bond formation. So this is seen in ethine. So 1 sp orbital will form a sigma bond with hydrogen, and the other sp orbital will form a sigma bond with the other carbon, and then the 2 unhybridized p orbitals will form pi bonds, which will lead to a formation of a triple bond. So hybridization can be used to predict the shape of molecules. So if you know the hybridization, you can predict the shape. Also, if you know the shape, you can predict the hybridization that's occurring. So Table 1 from our Cognitive textbook summarizes the relationship between the molecular shape and hybridization. So if you have two electron domains, your shape will be linear, or the electron domain geometry is linear, the shape is linear. An example would be carbon dioxide. So the hybridization for that would be Sp. If there are three electron domains, the electron domain geometry is trigonal planar, the molecular geometry is trigonal planar, BF3, BCl3, and so on. The hybridization is Sp2. If we drop down to 4 electron domains, the domain geometry would be tetrahedral, the shape is tetrahedral. If you look at methane, we have Sp3 hybridization. So it doesn't have to be just with carbons and hydrogens that you see this type of hybridization. It's for any type of molecule.